This is grade 12 University Physics, Unit 4, the wave nature of light, Lesson 4, the double-slit experiment. Question. A student performing Young's experiment with a single color source finds the distance between the first and seventh nodal lines to be 6 centimeters. The screen is located 3 meters from the two slits. The slit separation is 220 micrometers. Calculate the wavelength of the light. So let's start with a laser, maybe not one this powerful, but this laser is going to be fired through two slits very close together, much closer than these pencils. In this case, 220 micrometers. And then a screen is placed 3 meters away, where we're going to get an interference pattern. Now the central maxima of the interference pattern is m equals 0. And then the first nodal line, or the first minima, is n equals 1. And then we have m equals 1 and n equals 2, and so on. Now the question says that the distance between the first and seventh nodal lines is 6 centimeters. Well, let's count. If we look at the first nodal line all the way to the seventh nodal line, you'll notice that we have 6 delta x values in between these. Therefore, 1 delta x is simply 1 centimeters. Now we can use these values into our equation, delta x over L equals lambda over d, and rearrange for lambda to get 730 nanometers. Bonus question. How would the interference pattern change if a double-slit experiment was done with monochromatic light underwater? Well, if we look at the universal wave equation, you can see that if the velocity of the light decreases as it travels into water, the wavelength must also decrease, as the frequency does not change by simply refracting into a different medium. And then if we go back to our equation that we just used, we'll see that as lambda decreases, the spacing between successive maxima or minimum, delta x, must also decrease, as we have not changed the distance from the slits to the screen, nor the spacing between the slits.